Hello everyone, welcome to another session of coding with your friend. In our last session, we were trying to implement the APIs for linked list, the similar kind of APIs that Java linked list has in case for C. And the way we were designing it is like just implementing function by function. It was very ad hoc. It was sort of like an experiment for us to understand what are the different operations we need for linked list. What was our objective out of that? So our objective out of that was to replace eventually all those operations with UTList. So as you can see on the left side of the screen, I have opened UTList, linked list macros for C structures. That's an ongoing series that I'm doing of understanding the UT star macros, UT hash and all, which are created by Troy D. Hansen. I found them quite useful. They can also be used across many online programming competitions. They are pretty lightweight. They are not libraries, just simple source files. So you can just include them with your code. Use those macros. I was not aware of that. Probably like if you are really comfortable using C for such contests, you might already be aware of that, but I was not. So I tried exploring them. The reason I started exploring them is because C does not have the usual library support that other languages have. For example, like C++ and Java have uh, quite a good amount of library support for these basic operations, but C doesn't have, and you have to do a lot of groundwork in C if you want to solve some basic problems. This macro set or a library, whatever we want to call it, sort of solves that problem by implementing many of those things that we might need. So my point was, if we create our spec, what are the things that we need from a linked list? And for a spec, I looked at Java linked list. Uh, let me let me actually close other tabs. So Java linked list, which has a bunch of functions, and many of the functions are not necessary because sometimes they want the list to work as a queue, the list to work as a stack. Those are, I think, fine. We can just expose the raw functions. And if I just quick do a recap of what are the functions we have so far, we have this struct list node, which currently contains only an integer val, which is one of the downsides. Like, we can only contain integer in our structure till now. We have a utility to print the list. We have an utility to add first, add last, add all of an element if you're adding from an array. Add at a particular index, you can find index of a value. You can find get first, you can find get last, remove first, remove last, contains, size, clear. So a lot of utilities. I'll also try to push this code to my GitHub repo after probably this session, and I'll try to attach the link to that in the description of this video. So you can also look it up the code once you do that. Cool. So there are three things probably we wanted to implement. Three functions, which I just kept the body here at the end of our last video. And after we do that, we sort of have like a spec compatibility between all the APIs that we need from linked list in C versus in Java. And then we would sort of try to replace them with utilist macro. So that's the agenda for the video today. Let's get started. So the first function that we want to implement is last index of. So we have passed the head and we have passed v. It's not a modification, so we don't need to pass the pointer to head. It's only the one level of pointer is fine. So that'll do a copy of the pointer. But I think that's fine for us. What we want to find is if there is any, and typically how last index of is defined is remove it finds the index of the last occurrence of the specified element in the list, or -1 if this list does not contain the element. One downside of our list structure is that we are only keeping a head pointer. At this moment, I'm not changing the behavior. If we have a tail pointer, it's much easier to traverse, but I think we can also work with a head pointer and find the last index of. So, what are the different ways that we can find the last index of? I think the simplest way we can find it using a head pointer is we will continue searching for that element uh, till the end of the list, and we will also keep a tab of what is the index which has that element, and every time we find a new element we'll just replace that index. So the last index that so the index at the end of the iteration will contain the last index. Let's see how I plan to implement that. So I'll keep the default value as -1, and what I will do is while head is not equal to null, we'll try to see if head is equal to v, and we also need to keep a sort of a loop index which we will increment every time we iterate within the loop. Then our index will be I. And then we can return index. So it seems a quite simplified implementation, but let's see if this will work through just logical check. So if we have like a one element list, and if the element is matching, like the V is there, so we will go inside, we will check if it is equals, and we'll put index is equal to initialization value of I, which is 0. And then we'll go out, so that is also fine. If we don't find that element, we'll just return -1. I think if we have like even multiple elements, we will just replace that every time, and we'll also incrementing I. I think it should work, but let's just check. So we have a bunch of utilities. So what we can do is, let's see what we are doing here. So we are adding values here. Let's comment these two functions out, otherwise it would complain. So basically we are inserting elements here. Printf add index I, okay, and then we are printing the list, so we are inserting this element, and then we're inserting an ad hoc element. I think this works fine for us for list initialization, because we will anyway need another list. So what we will do is we'll do a printf and then just call this newly added function with, let's say, 30, and we'll see what comes out. I'm sorry, yeah. So we have to put that formatter here for printf. Let's clear it. So we are actually going into an infinite loop, which means there is something that's problematic happening here. The error that's happening is because we are incrementing the loop index, but we are also not actually iterating over the list. I think it's already saved. Let's run again. So now I think we have found the index is equal to 2. Just I think for our clarity, we can just do a printing like this. So index is 2, and that is sort of right. We can do, let me actually copy a bunch of things. So we can say, let's say where is 35, where is 10, where is 36, which is not in the list, and let's say 50, 500. Yeah, okay. So the last two should return -1 for us. The other guys should return proper values, like 30 is here, 35 is at index 5, 10 is at index 0. So this is actually working for us. What we can potentially do, this is just finding the index of, but not how do we know this is the last index of. So we can change this 30 to be like this. So now let's run it. Now I think we can see that we have 230 and the answer has changed. Now the index is at 5, which is exactly what we expect because there are two indexes of 30 now and we're getting the last index. So this is sort of done. Now the next function that we want to implement is clone. So clone, essentially, if we just look up what clone wants us to do, returns a shallow copy of this linked list. The elements themselves are not cloned. Um, so basically, we will just allocate new memory and we'll just copy the value of the entire list. So we will use the same setup. We don't need these many printf statements, but we would sort of have this same list and we would try to copy into a different location. To prove that we are actually copying to different location, we probably need to modify this function to also show us the location where it's stored. So for example, if I run this, it shows me the address of where it is stored. And as you can see, the address remains same across every iteration. And we are just allocating a newer address and putting a new value there. So we have modified our print list function. We don't want these many print lists, but instead just this add index. Let me see. Yeah, I need a semicolon here. So, yep, and similarly, I don't think we'll also need this. Yeah, so we just got this. One useful thing probably we can do, since we are printing there, that we can maybe do a new line. I think it will be cleaner to look. Otherwise, it's very tricky. So we have storage allocated like this, and then we are putting those values there. What clone should do, it should create a new list and it should allocate all the values that are there in this particular list. So what we can do here, need to return a new head. Um, let's see how we can do that. So we need to allocate a new location. So probably we can pass a head pointer. That's, I think, better. A second head pointer. So it could be like, we can call it source and destination kind of thing. And it should be a void return type. So the source pointer will have the original list and the destination pointer will have the new list. The destination pointer actually needs to be a pointer to a pointer because we are going to modify it in place. So what now happens is we have another, let's say, list. Let's call it head1, which is also null. And cloning is actually easy for us because if we already have the value, all we need to do is iterate over the list and just add that element at the end of the destination. And we already have an API to do that, add last. What add last will do is like it'll create a new location, it'll If it is null, it will take care of that. If it is not null, it will also take care of that. So let's test our assumptions there. So what we would do here is while source is not null, we will add last destination and source value. We'll just do source next, and I think that's it. Should be fine. What we need to do here is probably once we do print list, we will do clone head address of head1, and then we do a print list of head1. Just clear it up. Okay. Seems working, right? So we essentially have two lists. Those are stored in separate addresses, so they are shallow copy, and we have new addresses allocated and all those values copied over. So that basically is our clone function, which is quite easy. This is an interesting function to implement. So we have a two array function where if we have like a list, we want to return an array. So in order to do that, first we need to iterate the list twice because we want to know how much value we want to put into the array. But I think there is a doubt. We cannot do a variable allocation to an array if I'm not wrong. So what I'm trying to say here is, let me just try to comment all this out. And we will try to do something like this. Let's say I have a value 5, and then we want to do a num val. I don't think it's allowed, right, in C? It does not take a variable because it doesn't know if val is initialized or not. Only if it's like probably a hash define 5, then it'll work. So it only works with constants. So that's, I think, one issue that we might have if we want to create an array. So I don't think we can create like a C-like array here. Maybe we can create a dynamic array, but I would like to come back to that later. So for now, let's skip this part, int to array, and we can come back to that later. So we can keep it also commented out if needed, but I think it's fine. Let's come back to that later. So we have like sufficient amount of utilities in our linked list. Our linked list is a single linked list which contains an integer, which is a simple one, and it has all those operations. Now we would try to go into the business of seeing how UTList works and how UTList can help us solve a lot of these problems. And I'm expecting a lot from UTList because when I was just browsing through it, it seemed like UTList can provide the option of using a doubly linked list. It can also have option like circular linked lists, which are very interesting. So let's just try to read through the instructions first, how we can probably start using it. And then what we would try to do is slowly replace all of these APIs with the UTList versions. So in order to do that, first let me create a copy of this file, or rather a new file, which should be fine. So let me call it linked utilist.c, and we can just put some template values here. And I believe we have the UT hash file. We need to copy the UTList.h file, which is inside the source. So we'll copy UTList to go back, UT hash exploration, UT hash exp. I think it's fine. So we got the utilist header file here, and we can also include this hash include utilist.h. Printf, let's welcome the new member. Hello utilist. Let me go back to okay, yeah, UT hash exp. UTList. Okay, so it compiles and it runs. So I think our inclusion works fine. So we have created our setup. Now it's time to get coding. This is a simple way we should include it. We already have downloaded it. Licensing is not required for us because this is personal code. Efficiency. Prepending elements is constant time on all list types. Appending is order n on singly linked lists, constant time on doubly linked list. The utilist implementation of the double linked list keeps a tail pointer in head previous so that append can be done in constant time. Order n on single linked list, constant time on double linked list, order n log n for all list types. Insertion in order n for all list types, iteration, counting, searching, order n for all list types. List elements, you can use any structure with these macros as long as the structure contains a next pointer. If you want to make a doubly linked list, the element also needs to have a previous pointer. So we need to have an element like this. So let's copy this over. I think this does not have any. We will start with a doubly linked list now because we are going one level up. So probably we'll try to see the benefits of using a double linked list in this video as well. And we are storing a character pointer name, which is essentially like a string. That is fine, we can store anything we want. You can name your structure anything. I'm calling it element, that's fine for me. Within a particular list, all elements must be of the same type. That is, I think, expected because we cannot have like different types within the same linked list. Flexible previous on next naming. You can name your previous next pointers something else. If you do, there is a family of macros that work identically but take these names as extra arguments, which is not necessary. I think prev and next is like quite a standard nomenclature. List head. So how do we define? So we define list head should be initialized as null. So list head is initialized as null. So we have initialized the head. Let me move this. Okay. So the list operations, what are the things we have? The list supports inserting or deleting elements, sorting the elements and iterating over them. So this is quite a lot and also misses something. But I think in our previous iteration we had a bit of duplication. So insertion, deletion, sorting, iteration should cover all the APIs that we wanted. Let's see actually. So first we will test out these APIs, how they work, and then we can create the same set of APIs using UTList. So let's try to do that. So we'll have LL prepend, we have DL prepend. So prepend means to insert an element in front of the existing list head. Is there any way to print? So there is no way to print. So we'll need the print utility. Let me copy the print utility. We will probably need to this is also like this. So we're also printing the address initially. Later on we can flip it. Printf backslash n. Okay, that's fine. Print list is here. We want to do an LL prepend, right? So this is reference. Let's see. Let's try LL prepend. Is it? So our head will be head and will be name. What is the error it's throwing? Okay, what it expands to. This is, I think, interesting. It expands to name next is equal to head and head is equal to name. So we have to give it a node. Okay, so it can't work with a raw value. So essentially we have to just copy over the first elements section. Let me just get it here. We can make it like an element pointer, new node. We can wrap a character pointer name such that if we copy it element, we'll create a new element. The name of that will be name here. The next will not be initialized, and we just return this guy here. So let's see. So like a new node, and then this should be like. Now we are fine. Then we will try to print list head. So it actually says it expands to new node, next is head, and head is equal to next. So essentially, we can read how the code is expanded. So if we had written the same way, we could have written it in a better manner. So I guess like that's another learning for us. We can also change our older implementation without UTList by seeing how UTList implements that. That's the learning, because UTList is implemented by a much smarter guy than I am. So it's a big learning for me as well. So let's say we have something like this. Now let's try to run it. So we have this incompatible thing. We need stdlib hash include stdlib, clear it up, compile again, it compiles more. So we got this. Basically a list is prepended. Now let's try to do with name1, name2, name3, and name4. We don't get that. So I think this does not work in that manner, but so what let's see what prepend does. We only have just the one element, right? So prepend means insert an element in front of an existing list head, if any, changing the list head to the new element. Append means to add an element at the end of the list. Where do we have append? So we have ll append. Let me change it to ll append really quick. I'll come to the other items, prepend lm and stuff. Ll append. Let's see if this works. So this actually works. So what does ll append expands to? It expands to do type of head, temp, then new node, name1, next is void pointer 0. If head is not null, then temp is head, while temp is equal to next. And temp next is equal to new node, else head is equal to this actually is quite similar to our append function, a little bit different. We can try to see how we go back here in our implementation and change it. But seems like this append is working. What I'm curious to know, what does this append to signifies? So append to says, is there any instruction for append to? Okay. If the pointers are different, then append to will work. Got it. Makes sense. Very clean APIs. Okay, I think we have like a good example here. We'll come to that example, but first we will try to explore ourselves. I still don't understand what prepend can work. Insert an element in the front of a list, changing the list head to the new element. Append means to add an element at the end of the list, so it becomes the new tail element. Concatenate takes two properly constructed lists and appends the second list to the first. And apparently VS 2008 does not support LL concat and PL concat. VS 2010 is okay. I'm curious what would happen with, I'm doing it on GCC. So add these two elements in head 1 and head 2. What I need to do is do LL concat head 1, head 2, point list head 1. Still works. Right. These two lists and then they are concatenated. Pretty neat. Okay. Prepend element. What does prepend element mean? To prepend before an arbitrary element instead of the list head, use the prepend element macro family. I think that LL prepend, if I understand prepend properly, it should, even if the head is, when the head is not null, it should not simply replace it with null. Am I using this in a wrong way? LL prepend. Why is this screwed up? So LL prepend, what it does is, so I have a new node and I point that next pointer to head, and then I just change head 1 to point to the new node. So we're not doing a function call, we're essentially doing an expansion here. So let's say if I just do this step by step, right? So it's just a one-step operation. So we have head 1 initially, and I have a new node. So I point that next node to head 1, and now head 1. So initially head 1 is null. I point the next node to head 1. I guess this is happening because I'm passing this as a function call. If I don't pass it as a function call, element new node is equal to new node. Right? If I just pass it like this, let's call it new 1 and new 2, new 3, new 4. I just want to confirm my assumption there, if it's actually happening due to that, or because actually the function looks reasonable to me. Okay, now it's working. Yeah. So, but this is append, but whenever I change it to prepend, they will fail. Okay. So I just modify this to prepend. So it's what's exactly happening. It's a function call, and these are macros. So macros will be inlined. So essentially, our code will be expanded. Because our code is getting expanded, we are actually allocating 2 elements. So what this does is now if we look at it, it expands to new 1 points to next is equal to head 1, and now head 1 points to new 1. So there is only one element, new 1. And if there are multiple elements, then the do while loop actually makes sense. Otherwise, the do while loop, every time we call new 1, we're allocating a new element, which does not make sense, and that's why we are getting the wrong results. So it's not a problem with the macro. So now if we do that, we get a list like this, and now LL concat also works fine. Perfect. One thing I would like to see is C expanded, or rather in C, expanded after macro expansion. Macro expansion. I guess GCC minus E should do that, right? GCC minus E link to UTList.c. So yeah, cool. Now I think this is how it should look like. So I think something that the compiler puts there, but essentially we have these are the macros which are expanded. So we have this is prepend function, this is pend function. Then we have printlist as a function call. Cool. So actually, because these are macros, the program becomes much compact, but they don't have the overhead of function call. So that's, I think, another important pattern for performance programming if we want to improve, like use macros, but there are downsides of it. I don't think that it's the right video to discuss about that, but let's actually start exploring other things. So we have checked like prepend, then prepend element. So if we want to prepend after an element, um, so prepend element before an arbitrary element instead of the list head, use the prepend element macro family. To append after an arbitrary element instead of the list head, use the append element macro family. I think to find that element, we need to see which element actually has that. So for that, search is needed, right? So the interesting part is we have a for each function for list. This is like superb. So can we replace our print with a for each? We should be, right? So let's come to that. The sort operation never moves the elements in memory, rather it only adjusts the list order by altering previous and next pointers. Also, the sort operation can change the list head. I think sort was an interesting thing which we did not explore in our previous set of API. The for each operation is for each iteration over the list item from head to tail, which essentially we are doing for print list. A user example is shown below. You can use just use the next pointer directly instead of the for each macros. The for each safe operation should be used if you plan to delete any of the list elements while iterating. Okay, this is super detailed. Let's see how the for each is implemented here. DL for each, exactly the same thing that we are doing. So let's actually replace our print list, the first function that we can replace with a linked list for each, where we can say, okay, this is head one, and then we have element E. I can just call it E. Uh, and this is super cool. Like you can do things like that in C. For each function where you can pass in like a statement block which would be executed for each of the elements. This is, I mean, insane. I don't know like why I did not know about this library so far, but this is like a revelation. Um, okay, I'm probably like exaggerating right now, but so what we are doing here is just to e name, something like that. Why is this complaining? So for each, we'll just replace it with a for loop. And what do we need here? Does it have to be? I think it has to identify E is undefined. Okay, identify UT is fine. Identify ELT is undefined. Okay, that's tricky. I think it is fine, right? So do we have to define the type? We have to, I think, yeah, I guess, yeah. We have to just define it here. So the problem that we are doing is we are thinking like initialization will happen inside the loop. This happens once you come from a Java, a C++ background to C, and you assume like the initialization will happen inside the loop iteration block. So basically we have to initialize it here, the variable, so the compiler knows like there is a symbol called E, which is an element type, and then once we do a for each, it should do its job, and we can just replace the print list. Just run it, and it runs. Yeah, it works. Probably the only thing that we don't have now is the ability to print the address. I think we can still do that. We can just replace the entire thing, right? We can just simply do this. Why not? Yeah, of course. So yeah, that's how I think we can do it. So it basically prints also the address and the name. If we don't want the address, we can just skip it, make it a name. We don't need our print list function. So that's also quite easier. So this is super fascinating. I mean, I'm in love with this macro. This is doing so much stuff in a very cool manner in a language like C. That's just amazing. Um, then we have the search operation, which is a shortcut for iteration in search of a particular element. It is not any faster than manually iterating and testing each element. There are two forms, the scalar versions of searches. Um, for element using a simple equality test on a given structure member, while the general version takes an element to which all of the lists be compared using a comparative function, which makes sense because you can either do like a pointer comparison, you know which pointer is there, but I think the scalar comparison makes sense. Otherwise, um, it I mean, how if you already know the pointer to that location where this is, I don't know how useful that is. So maybe the scalar version will be useful for us. So let's see, LL search scalar. So what this does, this has head and it has element, it has member, and then the value. So let me try to see how we can do it. We can do an LL search scalar in head 1. And let's say I'm trying to find E. The member is my name and the value is name 1. Does it compile? It compiles. What does this expand to? So this is super powerful. So it expands to, I think C macros are probably like most underused and these libraries expand using it. So we initialize it with head 1, then we see until if E is not null, and then but I guess like the problem will come is this equals check. That's I think the problem that'll come. Because if it's a scalar value, String comparison will not work here. So that's normal. I don't think we'll find any value here. Let's just do a printf of ideally we could define like a comparator block. Printf percent s points name if is not known. And actually I'll make sure is null, not here but before here. So let's see. It found name one. Found the string comparison. 7 4. So probably I'm missing out something. Does C allow this string C comparison? How do I compare strings? So if I have, let's see, so maybe 2 character pointers can have, right? So if I have a character pointer C1 containing name 1 and I have another character pointer C2 versus D, I think quality should be a numeric. I think it's coming as 1. It is matching. So even if 2 character pointer char pointer equals C, char comparison C. So string comparison. So what does string comparison do then? This is such a dumb question. Like if I have a why do I need string comparison? Why do I even need it? So you have character key apple, character buffer, guess my favorite fruit. Let's run this program. I'm curious. I think we are just getting a bit off track here, but I'm sort of startled. So I'm just testing this thing out. strcmp.c. Let's answer. No, it's correct answer. So we are doing string comparison here, but instead, if we just do key is equals to apple, while key is not equal to buffer. Will this work? It doesn't. Why? Because why it doesn't work? So essentially, let's say print all those, both of them, pointers, percentage, key, buffer. So those two are same. But here, once we do this, what if like this? This is not matching. This is actually very confusing. So if we have like a character pointer and there are two same strings, is it because these are constants? And the way we store constants, they are same. Should we just see the location of these guys? Are they pointing to the same thing? If the values are same. I think it's because of that. So this is, I think, another interesting thing that we learned is why is even in case of a string, why is LL search scalar working? Because my assumption is once we do that if ename is equals name2, how do we actually compare them, right? Because if we have two character pointers should just compare the memory locations. And what happens is, like, if we allocate constants, and the constants are, I believe they are allocated somewhere in a separate location in heap so that we get like the same reference for all those values, and that's why the equality is working. And that's what we saw here. They're essentially the same pointers, even though we are seeing just name one here with character C1, character C2. They're essentially the same pointers. We just change the value. And they're still the same pointers. This is weird. Oh, my bad. Again, full experiment. See, same pointer. The previous one was that by my mistake, but now we'll change the constant value. Different pointer. And there is mismatch. So this is why it's working, because we are allocating a constant, things are changed. And when it's allocating from heap, like when you are dynamically allocating that memory, everything changes. So pretty big assumption, but it works. It works. So I think we are just at the 1 hour mark, and I believe we have covered a good amount of this library, and we are already able to prepend, append, do for each, which I think it's amazing, to concat and even do search scalar kind of operations on single linked list with very small amount of code. So I think that's good enough for today. Let's again huddle up in the next session and learn more about this UTList and UT star libraries. Thanks for joining. See you in the next session. Goodbye.